Hello, gentlemen. Welcome to week 3. This chapter is actually a really fun chapter. I actually enjoy this material. This is on. We're going to start on exponential functions. We're also going to talk about logarithmic functions. And I will tell you that this is really where we're starting to get into some of the functions that we're really going to want to know well. So when you go to calculus, you have a good understanding of them because they will pop up over and over again. So make sure that we get a good foundation here. There's not as much material in terms of section numbers that we did in the past in chapter 3, but certainly going to be a little bit more practice, and I want to make sure you guys really have a good understanding of the material. Alright, so let's get started. Let's talk about exponential functions. An exponential function is one in this form, a to the x, where a is called the base of the function. It's just a number. It has to be greater than 0 and it's not equal to 1. So, functions such as 4 to the x, for example, is what we call an exponential function. And x can be any real number. Okay? And so we wanted to see, let's learn about that function a little bit. Oh, there's my 4 to the x example. So if I plug in 2, it's 4 squared, which is simply 16. If I plug in 3, it's 4 to the third power, which is 64. If I plug in a half, remember that from exponents, I hope that this 4 to the 1/2 is the same as the square root of 4, which is equal to 2. Okay? So there's a quick example of exponential functions. This is the graph. All exponential functions sort of have the same shape if a is greater than 1. Now, how fast they go off to infinity and how fast they approach this horizontal asymptote depends on the value of a, as we'll see in a little bit. But let's look at the situation where a is greater than 1. Okay. The domain, there's no restriction on the domain. Domain is all real numbers. The range here, you should note that if I have a positive value of a, and a was greater than 0, no matter what value I plug in here for x, it's never going to be negative. Okay, so the range here is always going to be from 0 to infinity, and we can't actually even hit 0. Remember that any number a to the 0 is equal to 1. Okay, and we actually note that fact because that's on every single graph, exponential graph. Okay. The y-intercept, as we just said, is 0, 1. The horizontal asymptote is going to be the x-axis. And if you think about this, let's just look at our 4 to the x example. As x goes off to negative infinity, what we have here is, let's look at this 4 to the negative, let's just say third for now. What that means, what that negative exponent does, is it puts it in the denominator. So this is really 4 to the third, like that, which is 1 over 64. Okay? And as this number gets bigger and bigger, as it goes off to negative infinity, this number in the denominator is going to be really, really small. And so we're going to approach 0. Okay? So it's going to go to 0 as we head off to negative infinity. Okay? Hopefully that makes sense. It's always increasing. The values are getting bigger as x is getting larger and larger. The function is growing, going up to infinity, always increasing, and it's continuous. There's no holes or gaps in this function at all. Okay? Let's look at the situation where I have negative x, a to the negative x. Okay? In that situation, you should understand, and we'll talk about this in a minute, but this, if you go back to our chapter 1, I think, this is going to be reflection about y-axis. Okay? And go back to our 4 to the negative x, 4 to the x. If I have 4 to the negative x, and then if I plug in a 4 to the negative third, well, that's just equal to 4 to the third, and that's going to give me 64. And so this is going to just keep growing as I'm going out onto the negative side. But if I'm in the positive side, if I go 4 to the negative third, now I'm on this side. Again, I get 1 over 64, and as x gets bigger and bigger, that negative sign is going to cause me to approach 0. Okay? Again, the domain is the same. It's negative infinity to infinity. The range, still 0 to infinity. The y-intercept is still 0 and 1. Horizontal asymptote. Now on the other side, in the positive side, we have that horizontal asymptote. Okay, and again, as we're getting, you can see I broke it down a little bit. You can see how quickly it approaches that horizontal asymptote of the x-axis. This function is now decreasing. Okay, it's getting smaller. As x is getting bigger in that direction, the function values are getting smaller, and it is still continuous. Okay, so make sure you understand the difference between a to the x and a to the negative x. Here's an example of how the base changes things. Okay, the larger the base, if you look on this side of the graph here, okay, the larger the base, the quicker we're going to go off to infinity, which should make sense. I mean, compare 4 cubed, which is 64, whoops, and 2 cubed, which is 8. All right, so the bigger the base, the steeper I'm going to be on this side. So if I had something like, 10 cubed, 10 to the x, I would be like that. Note the opposite is true, that it's also, even though it's going to go to infinity faster, it's actually going to approach that horizontal asymptote more quickly. Because again, if you look at 4 to the negative third, that's 1 over 64 as we've talked about, and 2 to the negative third is 1 over 8. Obviously this number here is smaller than that one, so it goes towards the horizontal asymptote more quickly. So when we're greater than 0, the larger the base, it's on top of the smaller base, but when we go onto the negative side, it actually switches. Okay? We just talked about the reflection again, because we know that when we have reflection in the y-axis, we have, if we have f of x and we want reflection in the y-axis, we get this, right? And that's what the situation is between these two. Okay, I have a negative x and an x there. If I have reflection in the y-axis, just again from our rules from before, way back, this is all shouldn't be new stuff to you guys. Reflection in the about the x-axis was simply if I had f of x, if I wanted to reflect about the x-axis, we went negative f of x. Okay, so that took whatever positive value and became negative, and that's what we have in this situation. Okay, again, these are just rules from before applied to the exponential function. Horizontal shift. If I add a remember horizontal shift was going to be when I had f of x plus h, I would get a horizontal shift. So when I have 2 to the x minus 1, I'm going to shift to the right 1 unit. Okay? Hopefully you guys remember that part of it. Remember, I always think about this point where it's 0, 1. Well, in order to get 0 in my exponent, I have to move that point this way, 1, because 1 minus 1 is 0. Okay? Vertical shift, oh, I'll get that out of the way. Vertical shift is when we're outside. Okay, we're not in the exponent, so if I had something, pen back, if I had f of x plus k, let's say, where I have 2 to the x here, there's my regular 2 to the x function. I'm going to plug in that x value, then I'm going to increase it by 2 like that. All that did was raise that up vertically 2 units. Okay. Here's some practice. I want you to read these pages. Look at these examples. Talks about the graphs. Talks about the shifting. And here is some problems that I want you to do to understand the exponential functions. Important things to know, fellows, is make sure that you understand the difference between a to the x and a to the negative x. Make sure that you understand domain, range, what the shape of the curve is, and what the behavior is going to be. Okay, that's going to be important as we start to build upon this. All right, fellas, any questions, make sure you email me. Have a good day.